Hello and welcome. We are going to be looking at case 4, which is nothing but what a simply supported beam that is carrying a uniformly distributed load of W per unit run over the whole span of the beam. So we are going to be dissecting this beam. So now on this beam we have a uniform distributed load. So we have a uniform distributed load on this beam. So we are going to be looking for the shear force, the bending moment, and the maximum bending moment. So the first thing we are going to be doing is we are going to be sectioning this beam. Let's take a distance x. We are going to be sectioning this beam. Let's take this point to be x, and the distance between B and point X will be x. So this is what we have. So now we can go further to begin our calculations. Now the whole length of this beam is AB. If we are to convert this uniform distributed load on this beam to a point load, we are going to be multiplying it by what? By the length that the uniform distributed load covers. That is the total span of the load. So if we have a load from point AB, we are going to be to convert it to point load, we are going to multiply it with the length of what? Of AB. So to convert this to point load, it will be nothing but what? W multiplied by what? The total length, which is L. So here will be what? This place will be WL. So this is what we have. This is when we are considering what? The beam from A to B. So this is what we have. So now we are going to be calculating what? The reaction at B and the reaction at A. So we have RB here and we have RA here. So this is what we have. So first we know that the sum of upward force is equal to the sum of downward force. So if we having considered that, we can say that RA plus RB will be equal to what? Now we have just one downward force here, of course, which is nothing but WL. So this is WL. This is what we have. So from here we can decide to call this equation 1. So next we are going to be taking a moment about point A. If we take a moment about point A, we are going to be multiplying. Of course, we know moment is nothing but force times perpendicular distance. So this is going to be RB multiplied by the distance L. Then we are going to be having what? We are going to be having our load here, which we have converted to point load as WL multiplied by what? Is distance. Now having converted this uniformly distributed load to a point load, of course it will be acting at the center of this beam. That is, the length from here to here will now be L over 2, which is what? Half of L and half of L. So L over 2 plus L over 2 will give us L. So if we are taking moment about point A, it will be what? RB multiplied by the total length, which is L. Then for what? WL, which will be multiplying what? Multiplying L over 2. So I hope you get that. So taking moment about point A equals to 0. Let's consider upward force to be what? To be positive, and then downward force to be negative. So like I said before, we have RB multiplied by L, and it will be minus what? Minus WL multiplied by what? Multiplied by L over 2. This is equals to what? This is equals to 0. So this is the same thing as what? RB multiplied by L minus what? L times L is S squared. So we have WL squared all over 2. Everything equals to what? Equals to 0. So we can take minus WL squared all over 2 to the other side. We have RB multiplied by L to be equals to WL squared all over what? All over 2. So let's divide both sides by L. So L will go here. One L here. It has gone. One L here. We have one remaining. So this will go with this, and RB will be equals to WL all over what? All over 2. So this is what we have. Now we know that from equation 1, RA plus RB is equals to WL. So we can substitute RB in that equation. So we are going to be having RA plus WL all over 2 to be equals to what? WL. So this is what we have. So we take WL over 2 to this side. We have RA to be equals to WL minus what? WL all over 2. So this is what we have. So we can take the LCM. If we do that, RA will be equals to 2 all over what? All over 2 multiplied by WL is 2 WL minus 2 divided by 2 is 1 multiplied by WL is WL. So this is what we have. So 2 WL minus WL is nothing but what? WL. So we have WL over 2 as our RE. So this is equals to what? WL over 2, which is our value for RA. So here we can just write this to be RB is equals to what? WL all over 2. And RA is equals to WL all over 2. So this is what we have. So that's that for our reaction at B and our reaction at A. So we are going to be calculating doing the shear force calculation now. So we say shear force calculation. So this is what we are going to be doing now. So now, to calculate the shear force, don't forget we have sectioned this part. We have from B to X, we have from B to C, and we also have from C to A. So now let's start. Of course, our shear force at B, from here we know that it will be nothing but what? It will be nothing but what? But WL all over 2, because this is the only force we have at this point. So we are going to be considering upward force as positive and downward force as negative. So if we do that, we can say that our shear force at B will be nothing but what? WL all over 2. So upward force as positive and downward force as negative. Now next, we are going to be looking for the shear force at point X. Now to do that, I'm going to be taking this section. I'm going to be drawing this section here so that you understand what we are doing. We are going to be looking for our shear force at X. So let's do that. So for our shear force at point X, so we have this as the beam. We have this point to be B. We have this point to be X. The distance is nothing but what? But X. This is what we have. So we have a uniform distributed load all over the span of the beam. Now, which is what? Which is W. We have a uniformly distributed load. This is W per unit run. So this is what we have. So now we want to calculate the shear force at B. Now don't forget, we know that the shear force at B here is nothing but what? S dot F comma B is equals to WL all over 2. So in order to get the shear force at X, just as we always do, first thing, we are going to be converting this uniformly distributed load to a point load. To do that, we are going to be multiplying the load, which is W, multiplied by the total distance that the load covers, which is X. So, and if we do that, the load is going to be acting at the center of the beam. So if we convert this, this is going to be what? This is going to be W multiplied by X, which is the distance. So this is our point load. So to get the shear force at this point, we are going to be what? We are going to be minusing Wx from WL all over 2. So the shear force at X will be equals to what? WL all over 2 minus Wx. So this is what we have as our shear force at X. So that will be that all for that. Now to get our shear force at C, we are going to be taking out this section too, so that you understand what you are doing properly. So let's bring out this section. So we have shear force at C. This is our shear force diagram that we have there. We have something like this. We have a uniform distributed load over the span. Now this point is what? Is B, and this point here is C. So of course this load is what? is nothing but W per unit run. Now we have the distance to be what? L all over 2. So this is L all over what? All over 2. So this is what we have. Now, in order to get the shear force at point C, we know that B here, we have a force here, which is the shear force here is nothing but WL all over what? All over 2. So in order to get the shear force at C, it will be nothing but what? WL all over 2 minus, okay, let's convert the point load first. We have not done that. So to convert this uniformly distributed load to a point load, just like we did here, we are going to be multiplying the distance by the load. So W multiplied by L over 2 will give us nothing but what? WL all over what? All over 2. So let me rewrite this. So this is WL all over 2. This is WL all over what? All over 2. So we still have our W per unit run here. So by doing this, you can see that we have converted this uniformly distributed load to a point load, and this point load now is acting at the center of this beam. So to get the shear force at C, it will be nothing but what? WL all over 2 minus what? Minus WL all over 2. So that's how to get the shear force at C. So shear force at C will be equals to WL all over 2 minus, we are putting minus here because we have already taken all downward forces to be what? To be negative. So we have minus WL all over 2. So this will be equals to 0. So at the point where shear force is equals to 0, that is where we have what? The maximum bending moment. So this is what we have as our shear force at C. Now to get the shear force at A, from here we can see what we have on the board here. We have a beam of length AB. So to get the shear force at A, it will be nothing but what? WL all over 2 minus what? WL. Don't forget, this is the total length of AB. We have already converted it to point load, and it's what? Nothing but WL. So to get the shear force at A, it will be WL all over 2 minus WL. So the shear force at A will be equal to what? WL all over 2 minus WL. So this is what we have. So these are our values for our shear force at all points on this beam. So from this place, we can further deduce this. This can be equal to, if we take the LCM, we'll have 2 all over what? 2 divided by 2 is 1. 1 multiplied by WL is WL minus what? 2 multiplied by WL is minus 2WL. So our shear force at A can be written as what? As WL minus 2WL is nothing but what? Minus WL all over what? All over 2. So that's all for our shear force. Now we are going to proceed to our bending moment calculations. So let's start. So we say bending moment calculation. So now we are going to be doing our bending moment calculation. Now this is a simply supported beam. So we know that our bending moment at A and our bending moment at B is going to be what? Is going to be 0. So we are going to be calculating, looking for moment at X and probably at C. But what we need most especially is a moment at X. So now to get our bending moment at X, we know that bending moment is nothing but what? Force times perpendicular distance. So the bending moment at X here will be nothing but, if we consider upward force to be positive and downward force to be negative, it will be nothing but what? WL all over 2 multiplied by what? Multiplied by the distance. The distance here will be nothing but what? X all over 2, because the total distance is X. I will bring this section down here now so that we'll find the bending moment at what? At point X. So I'm going to be drawing this section down there. So this is what we have. Bending moment at X. This is at section X. This is what we have. Let's take this to be our beam. We have this here to be W. We have here to be X. we have the total length to be x. We have a uniform distributed load over the span, which is what? Which is W per unit run. What do we have again? We have our force at this point to be, our reaction at this point to be nothing but WL all over 2. This is equals to what? The reaction at B. Now, we want to find what? The bending moment. Now, of course, before we do that, you know that we need to convert what we have here to point load. So this will be, converting this to point load, we will multiply what? The force by what? The total distance on which the uniform distributed load covers. So this will be what? This will be nothing but W multiplied by X, which is what? WX. I hope you get that. So that's all for converting the uniform distributed load to point load. Now, to get the bonding moment at X is nothing but what? Force times perpendicular distance. So we have what? WL all over 2, that is taking upward force to be positive. We have WL all over 2 multiplied by what? Multiplied by the distance. Now, if the total distance here is X, and we know that when converting this uniform distributed load to point load, the point load will be acting at the center. So if the total distance here is X, it means that from from the center to the left hand side will be what? X over 2, and from the center to the right hand side will be X over 2. So we can say here is what? It's nothing but X over 2, and here is nothing but X over 2. So this is what we have. This is what we have. So this is what we have. So from the center to this point is S over 2, and from here to here is X all over 2. So to find the bending moment at point X, it will be nothing but what? WL all over 2 multiplied by X minus what? Minus WX multiplied by X all over 2. So this will be bending moment at X will be equals to WL all over 2 multiplied by what? Multiplied by X minus WX, which is our what? Our point load, multiplied by what? The perpendicular distance, which is what? X all over 2. So multiply by what? X all over what? All over 2. So this is what we have. So let's clean this part even as we solve further. So let's solve further. So our bending moment at X will be equals to, we have WL multiplied by X, which is what? WLX all over 2 minus what? We have WX multiplied by X, which is WS squared all over what? All over 2. So this is what we have as our what? As our bending moment at point X. So our bending moment at C will be what? It will be nothing but WL squared, WL all over 2 multiplied by what? L all over 2 minus what? WL all over 2 multiplied by what? So let's bring out this diagram here so that we'll be able to do that. So we have bending moment at C. So this is what we have. This is what we have as our bending moment at C. We have here to be B, where RB is equals to WL all over 2. So we have here to be C, and we have the total length to be what? L all over 2. So this is what we have as L over 2. So we have a uniform distributed load, W per unit span. So first we are going to be converting what? We are going to be converting the uniformly distributed load into point load. So it will be nothing but what? We are going to be multiplying W by the total length, which is L over 2. So here will be L WL all over 2. So this is what we have as our point load. Now to calculate the bending moment, it will be nothing but what? WL all over 2 multiplied by the perpendicular distance, which is what? L over 2. Then we have what? WL all over 2 multiplied by what? Half of L over 2. Half of L over 2 will give us what? So we have bending moment at C to be equals to what? WL all over 2 multiplied by what? L all over 2. Now, of course, we have already established that upward force will be positive and downward force will be negative. So that's why we have here to be positive. So we have minus. Now, the next force we have here is coming downward. That is minus WL all over what? All over 2. It will be multiplying what? It will be multiplying. So this is going to be what? This is going to be L all over what? All over 4. And here is going to be L all over what? All over 4. So I'll come again. We took a section, this section CB, we took it here. So to explain better, we know that the section length is L over 2, this is L over 2, and it has a uniform distributed load all over its span. Now this load is nothing but what? W per unit span. So to convert the uniform distributed load to point load, we are going to be multiplying it by what? Its distance. So the distance is L over 2. So W multiplied by L over 2 is nothing but WL all over 2. Now, don't forget, after converting this uniform distributed load to point load, it will act at the center. So if it acts at the center, the distance from the center to the left hand side will be what? Will be half of the whole length. That is L over 4 and what? And L over 4. So now let's go ahead and calculate the bending moment at point C. Now, the bending moment at point C, we are taking what? Upward force to be positive, downward force to be what? To be negative. So this is what we have. So this will be our force at this point, which is what? WL all over 2. So bending moment at C is equals to WL all over what? All over 2 multiplied by what? The distance, because bending moment is what? Force times perpendicular distance. So we have L all over 2, which is the distance from here to here. So this will be what? Minus what? Minus WL all over 2, which is acting downward, multiplied by its perpendicular distance, which is what? L all over 4. So this L all over what? All over 4. So this is what we have. So we can just do this simplification. WL all over 2 multiplied by L over 2 is nothing but what? WL square all over 4. WL all over 2 multiplied by L all over 4 is nothing but what? WL square all over what? All over 8. And the LCM of 4 and 8 is nothing but what? It's nothing but 8. So 8 divided by 4 is 2. 2 multiplied by WL square is 2WL square. 8 divided by 8 is 1. 1 multiplied by WL square is WL square. So our bending moment at C is equals to 2WL square minus WL square all over 8. Now, if you minus this from this, what will you have? You will have WL square. So this will be equal to WL square all over what? All over 8. So this is our bending moment at what? At C, which is equal to what? WL square all over 8. Now, if you will recall, okay, let's arrange our values here first before we simplify further. So let's outline our values for the bending moment. So we said bending moment at B is equals to 0. Bending moment at A is equals to 0. Our bending moment at C, if we calculated it to be what? WL square, which is WL square all over what? All over 8. So that's what we have. So now, if you come back to this diagram, for our shear force at C is nothing but 0, and bending moment is maximum where what? Where shear force is what? Is equals to 0. So our bending moment at C will be what? Will be the maximum bending moment, because at C shear force is what? Is 0. So at C shear force is 0. So our bending moment at C will be what? Will be maximum. So now let's draw the shear force and the bending moment diagram. So at all points where I have my force, I'm going to be representing them with a dotted line. So this is what we have. So this will be my reference line for shear force diagram, and this will be my reference line for bending moments diagram. Now at bending moment at B is nothing but what? It's nothing but 0. Shear force at B rather is nothing but what? It's nothing but WL all over 2. WL over 2 is positive. So let's go upward. Let's take this this point to be what? To be WL all over what? All over 2. So this will be WL all over what? All over 2. So this is what we have. This is WL all over 2. Now, of course, we have a uniform distributed load over the span. Converting it to point load is what? Is WL. So from this span to this span, we are assuming that what? So now we have our shear force at what? At the center to be what? To be C, which is what? Which is 0. So our shear force at C is 0, and our what? Our shear force at A is not, is minus W L all over 2. So our shear force at A will be what? Will be negative. Our shear force at C will be what? Will be positive, and our shear force at A will be positive. So I'll be drawing my line even up to point 0. So let's take, this is our point C. So we are coming back to 0. So first at C, you can see that it's nothing but what? 0 here. Now we are using we use an inclined line because we are having a uniform distributed load. For when we have point load, if you can recall, we use what? Straight line to represent it. But now we are having a uniform distributed load, so we are representing it with what? With an inclined line. Good. So our shear force at C what? Is 0. So our shear force at A is nothing but what? Minus WL all over 2. So of course you will know that minus WL over 2, you can just take this point here to be our minus WL over 2. So all we just have to do is to trace it downwards. So this is it. So this point here will be what? Will be our shear force at what? At A. So I hope you get that. So for our what is it called? For our bending moment now, we are going to be using the values we have there. So of course you know that this is positive, this is negative. So all you just have to do is to shade this part and also shade this part. So that's all for now. So our bending moment diagram, we know that bending moment at B is 0, bending moment at A is also 0. So our bending moment at C now, which is the maximum bending moment, is what? Is WL square all over 8. Now don't forget, I explained earlier, bending moment is maximum at what? At the point where shear force is what? Is 0. So bending moment is maximum at what? At 0 shear force. So we are going to be drawing our line upward. Now for inclined line on the shear force diagram, we are going to be representing it with what? A parabolic curve on the bending moment diagram. So we have bending moment at C, maximum bending moment at C to be WL square all over 8. So we just take this point to be WL square all over what? All over 8. And we know that also at A, our bending moment is 0. So we just draw a parabolic curve at this point. So how do we do that? We are just going to take the curve from here. So let's take this to be our parabolic curve. So this will be our bending moment, and this will be our shear force diagram. So I hope you understand how to get shear force and bending moment for a simply supported beam that is carrying a uniform distributed load of W per unit run over the whole span. and I hope you understand also how to get what the maximum bending moment. The maximum bending moment can be found where the shear force is equal to 0. So the maximum bending moment can be found, like I said, where the shear force what is equals to 0. So this will be our maximum bending moment. So our maximum bending moment will be equal to what? It will be equal to W L square all over what? All over 8. So thank you for watching, and stay tuned for what numericals even on this case. So thank you for watching.